So let's use differential equations in an applied setting. So copy all of this down and pause if need be. Okay, so we have y is the number of cases, and t is measured in weeks, where t equals 0 is March 9th. Okay, so we're going to make an assumption here. It's a simplifying assumption, but reasonable. We're going to assume that the rate of change of the number of cases is proportional. This little fish symbol is proportional to how many cases we have. So this is a reasonable assumption. Okay, what I'm saying here is that the more cases I have, the greater the rate of change of the number of cases. So the more cases you have, the faster the virus is reproducing. Okay, so in math, proportional means dy dt is some constant times 1. Now, we're going to do what's called a separation of variables here. When we want to solve here, we would like, of course, to get a function, y equals something. But we're going to solve this in order to find y. And we're going to be using our data up here. So we'll do what's called separation of variables. So how does that look? Well, you see you have two variables here. You have your y and you have your t. K is not a variable, k is a constant. So y and t are the variables, we want to separate them. Okay, so we're going to do something a little bit magical here, but it is all justified. We're going to treat this like a fraction and put our y, all of our y's on the left-hand side and all of our t's on the right-hand side. So this is called the separation step. So we get 1 over y dy is equal to k dt. So this is called the separation step. So I did a separate. And the next step is to, well, you're probably thinking it already. These look almost like integrals. All they need is the little integral squiggle in front. So we'll do that. Is our next step. Oops, it's not a integral symbol. So separate, integrate. So now we'll perform the integration. Here I get ln of absolute value of y. Is equal to, what do I get here? Kt plus a constant. Now, you'll notice that when I had two indefinite integrals. So technically you should have a plus c over here and a plus c over here. So what we do to simplify is we just combine them into a single plus c, which appears at this step here. Okay, now we can write down the data that we have collected. So we're going to take y of 0 is given to be 643. And y of 1 is 43, 43, 43, 43, 43, 53, 43, 53, 43, 53. Okay, this data will typically be given earlier in the question. So what we're saying here is that initially, March 9th, there were 643 cases in the US. And then 1 week later, went up to over 4,000. Okay, so we're going to use this information to find K and C. First of all, use this one first. So when T is 0, Y is 643. So we get immediately C is equal to ln of 643. So we'll need that later. That's good. And then when T is 1, we get 4353. K plus C. So K is equal to this guy minus C, which is given above, ln 4353 minus ln 643. Boop. Can you see that? Ln 643. So K is equal to ln of 4353 divided by 643. Okay, we have our K, we have our C. So we're in good shape. Now we can actually solve for Y up here and get a meaningful equation for Y. So what do? So what I'm going to do is I'm going to go E to the ln Y is equal to E to the KT plus C. And then E and ln are inverse functions. So they cancel each other out, giving me just absolute value of Y is equal to E to the KT plus C. Now, Y is a positive number, right? Y is a number of cases, so I can drop the absolute value. Don't need that. And what else can I do? I can write this as E to the C, E to the KT. So Y is equal to E to the C, E to the K with the T outside. That's a K down here. So why would I do that? Because if I look up here, I can see that E to the C is just 643. And E to the K is just this thing with the ln deleted. Because remember what I'm doing is I'm sticking an E right here, sticking an E right here, and then the ln and the E cancel. To the power of T. So there's my function. I have Y given in terms of just T. Okay, so we're able to solve our differential equation here. And how do we do it? We, first of all, separate. Then we integrate. And then finally, we celebrate. Integrate, celebrate, separate, integrate, celebrate, separate, integrate, celebrate. This is a very useful thing, right? Because we can just find the number of cases, well, an approximation for the number of cases, and very quickly just by plugging in a t. So for example, if I plugged in, say, 2 here, so if I plug in 2 here, this is roughly 29,500 cases. Now, the actual data, I believe, was somewhere just over 34,000. So, not a great model, because our initial assumptions were too cute. Just life isn't so simple as just bringing it down to a single assumption. But it's not absolutely horrible, and I think you'll agree that with some extra assumptions and some extra sophistication, this technique can be improved, and we can obtain more accurate models.